So today we're going to do more Fourier Sine Fourier Sine series and Fourier series. So we're going to do some computations on the computer. I'm just going to put this up to get some formulas down. So the objectives, I guess. So understanding Fourier series. Series. Fourier Sine series. And I guess Fourier cosine series. And I just want to remind you guys, yeah. Yeah, sure.
Just real quick. Just like the first one.
Oh, I did one of them, I think. So I did something like the last time.
In the last class.
I did something very similar to one of those problems, like one of the Fourier expansions. Yeah, in the last class I did. But if you have another one, I can. Oh, yeah, I forgot to ask you guys. So how did the boundary value problems you're talking about? So so did you guys try them? Yeah, everyone. And so some people. So you would like to see another one, and other people would like to see other ones with derivatives. Okay, so how about I do that next class, and we'll do the quiz for that on Monday. Oh, let's see. So, okay, so we're gonna have a quiz on Friday on maybe 14.1 for this. Okay, so let me just say quiz Friday on section 14.1. So this is just the like basic orthogonal functions thing. And thank you for telling me about the boundary value problems. So boundary value ODEs, I guess I'll do an example tomorrow or on Friday after the quiz. And then on Monday we'll have the quiz. So Monday we'll have the boundary value. Oh, we Monday then I guess Wednesday, next Wednesday. Boundary value. Oh, because it's President's Day, right? So boundary value quiz. Okay, so this is what it'll be, and I'll do one next class. Is that okay? Okay. I also want to remind you guys that there's the surveys. So okay, so there's the one that I posted on Piazza. So so I think 5 out of 9 people have answered. And then there's the SEM survey, which they just sent out. I think they sent it out Monday, and 2 out of 9 of you have answered. Right, and so if they get to 100% on this one, you get half a quiz score. If you get 100% on this one, you get half a quiz score. So if you guys fill out both of them, you'll get a free quiz. Okay? And so I think we're up to quiz. Are we up to quiz 5 now? Or quiz? We took quiz 4, I think. And then so after our 5th quiz, we get to drop 1, and this will count as a free quiz. If you don't fill that out, I'm not going to like mark you down or anything. Okay? So it's just a free quiz. We've done 5. Okay, so you drop your lowest one already, right? And now I guess this will be 6, 7, and then this will be a free 8. Okay, if you guys can do it, and that'll be by Monday. Okay. All right. Okay, so so what I wanted to do today is I wanted to do the computer stuff. So that's what I prepared for today. Was I wanted to show you. So we ran through that computation, kind of like tornado, right? And computed a Fourier Sine series, 2 Fourier Sine series, in fact. Did we do 2 or 3? I think we just did 2. And so let me remind you guys what these formulas were. Okay, so So let's recall. So I'm going to work on this half real quick, and then I'm going to go do it on the computer again. Okay? So there's a bunch of formulas that we're going to need. All right. So so we had the formula for expansion in terms of orthogonal functions. They have to be, well, we'll see. Right? Okay, so and it said that f, okay, so we had some sort of approximation symbol that this was the sum from n is equal to 0 up to infinity of, so I'm supposing I'm indexing at 0, so you could have some other indexing if you want, over phi n x. Okay? This is what we had. Okay, so in the case, so we figured out what our eigenfunctions were from this vibrating string problem. So we had this interval 0 to 1, and then we had these functions phi n was sine n pi x. N starts at 1, 2, 3. So notice like the indexing here doesn't really necessarily have to correspond to the indexing here. All right? And we had that this inner product defined in the following way. So this was the integral from 0 to 1 of f of x g of x dx. Okay, so we had this special case, and then we had this was our basis here. We figured out that what the sine series was for the function 1, right? Sine series for f of x is equal to 1. All right? And this was the following thing. And I'm going to write it down now. So it's the sum from n is equal to 0 up to infinity of 4 over 2n plus 1 pi sine of 2n plus 1 pi x. Okay? And this thing looked like 4 over pi sine pi x plus 4 over 3 pi sine 3 pi x plus, let's say, 4 over 5 pi sine 5 pi x, something like this. Okay, so it was only the odd terms that showed up in the expansion for this thing. All right. All right, and then we had another one here. So this is supposed to be like 1, right? But you can see that like on this side here, this is a sum of sines, right? So it's like somehow periodic. You can see that this function here is odd, right? If I plug in a negative, it's a sum of odd functions, right? This is not an odd function, so something weird's going on, okay, with the convergence of this. So I'll show you what's going on with that, okay? And then so we had the sine series for f of x is equal to x. Okay? And so here we had that x, and so we have this, it's 2 sum from n is equal to 1 up to infinity of 2 over n pi negative 1 to the n plus 1 sine of n pi x. Okay, so these were the coefficients. These are like these coefficients here. And this is our function here, sine. Okay, so yeah, this is what we'll get. All right. So now I kind of want to show you how this works on the computer. Okay. All right. And okay. All right. So we wanna kind of write out what this thing is here. Okay. So we're gonna write out what this series is. Let me show you how to work with Sage a little bit. So like, you can make an array 1, 2, 3, 4 here. 1, 2, 3, 4, right? And to some things, so let's call this I don't know, a list. All right. Okay. You can do sum list. And what it'll do is it adds all the numbers in the list. So this is one of the commands you can have, right? Other things you can do is you can plot functions. So plot, right? And you can do, so x is always a variable in this thing. So you could do, say, plot pi. Pi is, if you do pi like that, it's like the constant pi. Pi x. And you do x, and we're interested in this interval 0 to 1 here, right? So I'm just going to plot what these things are. So this is the first one. This is the graph of this first thing. So it's the first mode for the wave problem that we did. We could plot some more of these. Let's say we plot the first 6. So we could say, go here, for n in range 1 to n. So it always starts at 0. So this is Python based. Okay, so this is a Python syntax here. You could do plot, I don't know, sine n times pi times x. X is in 0 to 1. And I think it should plot a big, long list of these things now. Okay, so it should plot all of these. Oh, sorry, for n in range, let's do 1 to, let's say, 6. Sorry. Oh, wait. Did I say n was 6? How did it know? Okay, well. Yeah, okay. So here's the first one. This is sine pi x. This is 2 pi, right? Sine 2 pi x, 3 pi x, and so on and so forth. Okay? So we're taking these functions here, and then we're writing, what we're going to do is we're going to write our function as a linear combination of these functions. Okay? So that's what this thing is. So it's like we take these sine waves and then we do them. And the idea is that the higher the frequency is, right, the more cancellation it'll have. So it'll be less, this term is the least important term, right? Because the high oscillations will give you cancellation. Okay, so that's the idea. Okay, so let's write out what our series is. So again, we can check that they're orthogonal. Okay, so we can do like an integrate command, right? So we could do sine, I don't know. Well, what do you guys want to do? We can check that the norms, for example. Let's do that. Sine pi times x. So what did we compute the norms were last time? Right, so the norm was the integral. So let me remind you guys what the norm is. The norm is the integral squared. Right, so let me remind you that. So we had this inner product here, right? And so that the norm squared here of some function, this is this thing, and it's the integral from 0 to 1, in this particular case, of f of x squared dx. Okay, so this is what's called the L2 norm. Or the L2 squared, this is the L2 norm here. Okay, so it's like this L2 norm squared. So really the norm is the square root. It's like the square root of the inner product. Okay, so this is what we're going to compute here is we're going to compute the norm squared of the first basis element, right? And that was 1/2, okay? And so what we could do then is like we could take this thing and we could say check that all the norms are the same if we didn't know. So times n here, like this, okay, for n in range, let's say 1 to 6. So I think it stops at 5. Okay, so they're all 1/2. So yeah, so let me just show you. Range 1 to 6. What is this thing doing? It gives you these numbers 1, 2, 3, 4, 5, right? And you could do it, you know, you can specify the starting point like that. If I were just going to say range 6, it would just be, you know, start at 0. Okay, so it would be the first 6 numbers. Okay, so that's okay. That's that. So okay, so how did we compute these coefficients for this one here? Okay, so this one. So notice that there's only odd terms here, right? The odd terms appeared because the even terms had cancellation. So what we're doing is we're taking a function. So let's look at this thing. So we're taking a function. We're integrating. Sine n pi x times x times u, let's say u, and we're saying u, let's put up here, that u is this constant function 1, right? And this goes from x is equal to, and let's say just for one example, n is equal to 1, right? Okay, x is 0 to 1. So what this does is this thing computes, so comments in Python are these, the pound sign of the hashtag. Hashtag integrate. No, this is inner product. Okay, so here, so what should this thing be? This one should be 0, right? Because this will be like the first coefficient here. Oh, let's see, that's not 0. What have I done? Oh, sorry, this is an odd term, right? So the odd terms are non-zero, the even terms are 0, right? So if n is equal to 2, right, that one's 0, right? So we could even say integrate this for n in range, I don't know, 1 to 20, right? Right, so we're getting these coefficients, right? These almost match up with these coefficients, but what's missing? So there's a factor of 2 missing, okay? And so where's that factor of 2 come from? So the factor of 2 that we're missing is this thing. So we have these things that are all 1/2, 1/2, 1/2, right? So these are the norms. So like here to 20. So here are the norms of these things, right? And then we have all of these. Then we have the top thing. So the top thing we've computed is this. The bottom thing. So all these halves are these things. And then the thing on the bottom are these here. So we need to take a ratio of those two things to compute the series. Okay? So let's compute the sine series for u is equal to 1. So really I'm doing this where this is u instead of f here. Okay? So this is the sine series for u is equal to 1. So let's do this. So we have, so let's make a list of them and then we'll sum them. Okay? So here we're doing integrate. Okay, so we're going to make a list. So we're integrating sine n times pi times n pi x times u. Okay, so let's specify some things. So u will be 1, and then we'll truncate the series at 10 terms, say. Okay, or we'll take the first 5 terms. We'll do the first. Let's do the first 6 terms. Okay. Okay, so we're going to integrate this thing from x goes from 0 to 1. All right, and then now we need to divide by, we need to integrate from sine n times pi times x squared. So we're doing the norm on the bottom. X is 0 to 1, like so. Okay, so then we have that norm. Okay, and for n in range, let's say 0 to m, or let's say 1 to m. All right, and then, so that should be that. Okay, so now I have this coefficient, and what do I need to multiply the coefficient times the basis function. So there's the coefficient times the basis function, if I did not miss parentheses or something. Okay, so this thing should be, should return the first couple terms of our series here. So this is 4 divided by pi sine n pi x, right? This is the next term here, this thing. This is the next term here. Okay, so these are our terms for this series. Okay, so let's give this thing a name. I don't know, we could call this SM, so the mth series. Okay, and then we can plot it. So let's say plot SM for, and then let's give a little bit of space. So let's go from like -2 to 2 and see what's going on with this thing. Okay, and so what should this thing look like before we plot it? Yeah, it should look like, well, it should look like the function that we're trying to approximate. F of x is equal to 1. The graph of f of x is equal to 1 is, well, you just set y is equal to 1, and you just go straight along. Okay? So that's what this thing should look like. Okay? That's what we're trying to capture, and we're trying to capture it on the interval 0 to 1. Oh, what have I done? What have I done? What's going on? Oh, there's a capital. Right. All right, there we go. Okay, so you can see this is like these couple terms, the first couple terms here of this series expansion. What it's trying to go is, here's the interval 0 to 1, and it's trying to approach this constant function here, right? So I think I can do something like this. If I do 1 like this. So here is so you can put a list of things in there, and it'll plot both of them. So here, right, it's trying to approach this line 1. Okay? What we could do is we can increase the number of values, and we should expect this thing to get closer and closer. So let's see. Let's go to 9. And there we go. So let's see. It didn't get much better. Okay, so let's do like 20. Okay, so you can get closer and closer, and you can see that like it's a better approximation here than it is on the outside, right? And that's called Gibbs phenomena, right? So this like bad convergence here. It's bad convergence, you know, because this thing's really not. And also note that this like I said, there was going to be an odd function. This thing is an odd function. It goes to like a step function here, and then it goes down, and it made itself odd, right? So it forced itself to be odd by approximating by these sine things. Yet the approximation on this interval, which is really only where we cared about where this function was defined, is nice. Okay. All right. So let's do our other one. Okay, so let's look at our other function now. Okay, so the other one that we had was this series here, the sine series for f of x is equal to x. Okay. All right, so let's do this thing, sine series for u is equal to x. Okay, so so it's really the exact same formula that we did, except we're just going to change out what u is, right? The denominator doesn't change, nothing matters. Okay, so here we go. So let's, I don't know. I'm just, oh, I insert. Okay. Oh, yeah, now I need to plot that, huh? Okay, so let's do plot. No, not in that cell. So you can do Shift Enter. So, by the way, do you guys know what website this is? So this was, so it used to be Sage Cloud, right? Now this is CoCalc. So it's Sage. You guys have probably heard of Sage, yeah? Okay, some of you, right? Okay, so so this is Sage. Sage is like an open source alternative to Mathematica, Maple, MATLAB. That's the idea. And so you can go on this web page. It's a little slow if you don't like. Well, it's okay for. I mean, there's a paid version of it that gets makes it a little bit faster, but yeah, that's what I'm using. And anyway, you can go use this, and you can just get a CoCalc account, and then you can use this thing. And there's lots of functions in there, but it's open source. It's pretty nice. So you don't. So like when you're out working, and you need Mathematica or something, and you don't want to pay $1,000 or whatever it is they ask, you can use this. Okay. So, all right, so let's plot this one for x is from -2, x is from -2. And the syntax, this is similar to the syntax for Mathematica. Go. Oh, let's see, tm. U is 1. We forgot to change this. Right. I guess we should also check that. What the heck? What have I done? Okay, well, there we go. Right, so here, the interval is 0 to 1, and now it's approximating here, and then it's got this jump because it's trying to make this like, I guess, 2 pi periodic with, or not 2 pi, but -1 to 1 periodic, and here it's trying to match what it is here. So, yeah, so I think at this endpoint it converges to the midpoint between here and here, right? So it doesn't necessarily converge at the endpoints. Okay, so you see what's going on with these things? This is the approximation, but it doesn't approximate the whole thing. It makes it a periodic function. Okay. All right. So there's an. So let's do a quick check to see if we can do something. So what should be? Oh, let's look at the terms too. Let me just do the quick terms here. Let's just see what this thing looks like. And so here, so here's our first term, right? So you can see the alternating business here. So n plus 1. So n plus 1 is going to be, so this is a positive term. You can see that this is the first term, it's positive. This is the next term, it's negative, right? And then you can see the pattern here, right? So you can see these coefficients here. Okay, so that's what we're reading off. Okay. All right, so what should be the sine series? So what if I put sine n pi x there? Like, what should happen? Like, so for example, let's do this one. I'm going to take this, put this here, and then what should happen if I take this to be sine pi times x? What should the series be? Yeah. It should be just 1. It should just return sine pi x, right? Because it's just one of its own basis vectors, right? So it's one of the basis vectors, and if we're going to try and expand it in terms of the basis vectors, it should just return the basis vector, right? So let's do that. All right, and let's see what happened. And see there, we just get the basis vector back, right? I could just take another combination of basis vectors, so 4 times sine, let's say 100. Not 100, because we're not going out to 100. Let's say 17 times pi times x, right? So this thing should return the same thing, right? So so if you put in a linear combination of those signs, you'll get a linear combination back, right? So this is one of the bases for functions on this interval 0 to 1. There are other bases of functions which I want to talk about as well. And I guess this is kind of something to consider that they don't really talk about in the book, but we won't really talk about it in this class. But in application, something to consider is what is the best basis for expanding a function in order to store the information efficiently, right? And this gets into these things called wavelets and things like this. So yeah, and so this is a kind of an interesting area of math is to like, okay, so you have a function and you want to be able to store this function, right, into a computer, but I want to store it with like the least amount of coefficients as possible, right? So how do you do this in a practical sense? And so this is, you know, it's an interesting area of math. Okay, so this is one basis. Let me do one more. Let me do one more. Okay, so notice here that it forced this function to be even, right? So let's see what happens if we take an odd function, like cosine n times, or let's say cosine pi times x. Okay, so this is an odd function. Okay, so it shouldn't be expressible in terms of even. I mean, well, it can be expressible in terms of even things, but this is the one that's like particularly weird to do because it's like we have a bunch of even things, right? And now I can take this odd thing and let's just plot it real quick. Let's say plot Tm for x minus 2 to 2. Okay. So this is another good way of like checking your computation. So if you have some series and you're like, this can't be right, right? What you can do is you can go just plug it into a computer, right? So kind of nasty, right? So this is it. This is it doesn't approximate very well. This is cosine, guys. Okay? So let's see if we can increase it to see if we can see the shape. Let's go to 100. More m. Okay. Yeah. Eventually, if you play with these things and you try to increase terms too much, it breaks, right? So it comes into a certain place where like you start getting lots of round-off error, and it'll just turn into noise, and you'll get junk back. Okay? It's kind of like in a calculator. If you do like 1 divided by 10 to the 16, you'll return 0, right? So is it going? It's working hard. Maybe 100 was a little much. Yeah. But this is, you can see how this can maybe become an issue when you're in practice, right? So like, if you're actually going to use this for something like in engineering, don't just use a Fourier Sine series or something. You know, like there's much better things to do than to use this example, right, of expanding something in terms of a basis. Okay, so now it looks a little bit better, right? Okay, so you can see it's this part of the cosine, and the errors are pretty bad done. The Gibbs phenomena is real, right? Okay. Okay, so now let's talk about another basis. Yeah?
If we change our domain to be like -1 to 1,
Mm-hmm.
if you're adding a bunch of signs together, how will you get x of 0 to be 1 for cosine?
So, so if you change the domain, you have to change the functions. So like, so we'll talk about that. So yeah, so if you change the domain, yeah, so that's a good question. So you always have to rescale, right? So for changing the domain, let's do that real quick. Okay, so the really basic one, so this is we could say it's sine, let's say sine x for x, sine nx for x. So okay, let me tell you, let me warn you here. there's something bad that can happen between sine nx and sine like 2nx. So let me see if this is right. Okay, so this is 0 to 2 pi. Okay, so let me make sure this is right. And this might be off by a factor of 2. Because, okay, so let me actually show you something for this one. For 0 to 2 pi, there's another basis that I wanted to talk about anyway. Okay, and the other basis is sine nx. So this is why this is wrong. Okay, and cosine nx with 1. Okay, so this is for n is equal to 1, 2, 3, so on like this. N is equal to 1, 2, 3, like this. Okay, and you can consider this is like the n is equal to 0 case. So these guys are the Fourier. This is what's called, this is a Fourier basis. Okay, okay. If we were going to shrink to the interval 0 to 1. Okay, so if we were going to shrink to the interval of 0 to 1, so so when x is in 0 to 2 pi, so we could do something like 2 pi t is equal to x. Okay, if we did this, so this is a change of variables here. Okay, so then we get a new thing. We get sine of 2 pi nt. So I just plugged in x here, right? Okay, and cosine 2 pi nt. And then we have this constant function 1, like this. And so this is the interval 0 to 1. Okay, so what you do is you rescale these guys to this to get this. So this is the Fourier basis. For this interval 0 to 1. Okay, let's go back to this thing. Okay, so here, notice that we had another basis for 0 to 1, right? The other basis that we had was the following. So the other basis we had was, so this is the Fourier Sine basis. And this is the one that we introduced first. It came from our vibrating string problem. And this is this sine of n pi x. So notice here that there's a 2 here, and there's not a 2 here. Okay? For n is equal to 1, 2, 3, 4, and so on. Okay? So the basic one here is nx over 2. Okay? So here, so what happens is, let's see. So this is right, I guess, because so sorry, we have to do this thing again, right? So let's do it with the t's again. So let's say this is with t. T is an element of 0 to 1. Let's do it like this. T is an element of 0 to 1. Okay. So to go back to the x's. So to get something here, let's figure out what this is. So to go from here to here, we have to use this relation, right? So x is 2 pi t divided by, x is equal to 2 pi t, which tells us that t is equal to x divided by 2 pi. All right. So now from here to here, what do we get? So we get sine of so n pi, n pi, and then we do x divided by 2 pi, right? And so this is equal to sine of nx over 2. Okay, so it was like that. Okay, so this is a basis for this interval now. Okay, so this thing here is the Fourier Sine basis. Okay, and the difference between this thing, these guys, and these guys, or let's say, so these guys and these guys is that here, notice that these guys are always periodic on this interval. Okay? This one here contains the things that are like the original one, which is like this bump, right? These ones here, they only contain full things. Okay? And so these ones contain like half things. Okay? Does that make sense? Okay? So and they also, and to make up for the ones, so to make up for the fact that these ones only have full periods, right? We throw in this thing and this thing. We have to throw in two extra, well, I mean, actually an infinite number of extra things. This cosine and this 1. Okay? So, so let's talk about, so in general, you can take the basis things in the basic ones and rescale them to get a basis for a new interval. So maybe let me just write that over here. And then we'll come back to this in a second. Okay. So so if you have a basis for, let's say, 0 to 2 pi, one can rescale your basis to get a basis for functions on the interval 0 to 1. Okay? So, all right, and so what do I mean by this? So here, so let's take this, 0 to L, let's say, or any other interval that you want. Okay, so you'll have to shift, and then you'll have to translate. Okay, so here, so what do you have to do? 2 pi divided by L t. So I want to make this right. So we're going to call x the thing in 0 to 2 pi. Okay? So I guess you can do x is 2 pi lt for t 0 to 1, or 0 to L. Okay, so this is the change of variables here. Okay? So, so for example, so what is the Fourier Sine basis for, let's say, just an interval 0 to L? Okay? All right, so here we have our Fourier Sine basis. So the solution. So the Fourier Sine basis for this interval here, 0 to 2 pi, right? This is sine pi x, n pi x over 2, like this. Okay? So then what do we do? Using the relation here, x is equal to 2 pi over LT, right? Sorry, this is not n pi x, this is nx. So I was worried because I would have gotten a pi squared. I'm using this one here. Yeah, because these cancel, right? This is this one. Okay, what do we get? So we get that sine, so n over 2, 2 pi over L, t. So this is our new basis. So we have these 2's cancel, so n pi over LT. Okay? And notice that when L is equal to 1, it agrees with our original thing, right? Okay. All right. Does this make sense? Does this answer your question, Adam? Oh, so you wanted to go from negative something to something?
Because otherwise I don't get how you'll ever get 1 when x is equal to 0. Like if that little interval is really important to me.
Okay, so yeah, so let me go, if we want to go from negative something to negative something, let me show you that, okay? So, so we have this one for 0 to 2 pi, and this one from 0 to 2 pi. This actually works for any branch of the angles, okay? So this also works, this one here, this also works for negative pi to pi, right? Or, you know, let's say theta naught plus 2 pi for any combination here. And here, theta naught is negative pi for this particular case. So to translate, does that make sense now? Okay. So now you can take this thing and move it to any interval that you want. Okay. All right. So this one, since it's it'll work the same way. Same thing here. So for intervals okay. Okay. So so I guess what we'll do next time is I'll do some Fourier expansions. Let me show you also another basis. One more while we're here. Let me show you one more basis. Okay, so we have the Fourier sine basis. Okay, there's also the Fourier cosine basis. So you could do the same thing with instead of sines, you could use cosines. Okay, but the thing is that you have to make sure you have the single hump, right? Not just all of them periodic. Okay, then you have this Fourier basis, and the best one, the one that all mathematicians like, is this complex one. So there's this complex Fourier basis. Right? And so here, you write functions here as c to the n, e to the I, n theta. So you can say theta is in 0 to 2 pi. And n goes from minus infinity to infinity. So the basis for functions on 0 to 2 pi is this collection. So you have 1 e to the I theta, e to the 2I theta, and then you keep going like this. And then you go e to the minus I theta, and e to the minus 2I theta, and so on. Right? So this is this is kind of the basis. This is one of the really nice bases to choose from. It's really easy to see that they're orthogonal, but you have to change the inner product. So the inner product here, and this is usually what we call, when mathematicians use the word Fourier series, this is what they mean usually. Right? An expansion in terms of this one. Okay? So the inner product here needs to change. Needs to change because it's complex valued. With C valued functions. And let me explain the rule. So here, fg is the integral from 0 to 2 pi of f of, and let's say we get f of theta, g of theta bar, right, d theta. Okay? And so here it's, so this is, if you guys have seen inner products with complex numbers, you need to take a complex conjugate here, right? And so this has the modified rule. That, you know, fg is equal to gf complex conjugate. Okay? And so sometimes this is called a Hermitian inner product, right? Okay, so this is how we measure the norms here. And so, yeah, so one of the things that we'll I guess I'll check this at the, well, after we do the boundary value problem, I'll check that this is actually an orthogonal basis, okay? Or that they're orthogonal. I won't check that they're a basis. So a basis means that you can always write a function as a combination of them, right? And so we haven't really said anything about that, right? We just have taken orthogonal functions and expanded them, right? I guess I'll say a little bit more about this, right? So look at chapter 14.1, and then we'll do the quiz on that thing next time.